Okay, welcome everyone to today's IQ seminar. We're really pleased to have Andrew Baczewski here from Sandia National Lab. Andrew is a principal member of the technical staff at Sandia and a research professor at the University of New Mexico, and he's a real expert in quantum simulation. He got his PhD from Michigan State, and then became a postdoc at Sandia, where he still is as a member of the technical staff. And with this, please go ahead.
Sure. Thank you so much for the introduction and the invitation. I'm excited to share some of our recent work today concerning quantum simulation of materials in extreme conditions. And if it looks like I'm looking off into the distance, it's because I have kind of a monitor and another monitor in front of me, which say that I'm happy to be interrupted in either the chat or online if questions come up in the process. I kind of have something set up to manage things. In any event, I'm going to be primarily telling you about quantum simulation of materials in extreme conditions as is relevant to inertial fusion. But at the very end of my talk, I'll allude to some astrophysical and planetary science applications that we're also thinking about at Sandia as well. So to kick things off, I'd like to start by acknowledging my collaborators. So today I'm primarily going to be discussing results from a collaboration with Google and a bunch of folks at affiliated institutions that appeared in the proceedings of the National Academy of Sciences back in June of this year. The title and the archive listing, in case you want free access, I suppose, are indicated on the slide right here. And this is, again, kind of a collaboration between two of us at Sandia, so myself and Alina Kononov, and a whole constellation of really stellar scientists at Google. The lead author here is Nick Rubin, but there are a ton of other folks who made excellent contributions on this as well. And as far as support on our end is concerned, this is funded by the National Nuclear Security Administration, the Office of Fusion Energy Sciences, and kind of our internal funding pool. So acknowledgements out of the way, let's dive into science. The promise of this talk is that I'm going to tell you something about quantum simulation materials in extreme conditions, and inertial fusion, specifically inertial confinement fusion, is the motivating idea here, which is to say that we would like to do quantum simulations that produce value for people trying to design ICF targets. So one such ICF target is illustrated on my slide right here. This is from a 2022 Nature paper by Zijlstra et al., kind of outlining some of the great successes that have been seen at the National Ignition Facility at the Lawrence Livermore National Laboratory in Livermore, California. And here on the left, you see essentially kind of the target itself, which is to say it's a hull round with a fuel capsule on the inside. And that hull round is going to be illuminated by 192 high-intensity laser beams that are all aimed essentially at the walls of this high Z metal target that is holding this fuel capsule. And that is going to cause the walls to essentially radiate X-rays. They're then going to exert radiation pressure that crushes the fuel capsule inside. That fuel capsule is a high-density carbon and DT mixture, which is to say that essentially the X-rays are going to crush that capsule in such a way that the density and temperature of the DT mixture increases until fusion starts to occur, i.e. Alpha particles are produced. Those alpha particles are then going to have some kinetic energy to their production, and they're going to redeposit some of that kinetic energy back into the burning plasma that produced them. And this is essentially one of the defining criteria for ignition, which is say that it's a condition in which the fusion reactions are the dominant source of heat here, kind of exceeding losses due to either conduction or radiation. This heating process is due to stopping power, though, and stopping power is the key thing that we're going to be talking about simulating on a quantum computer today, right? But kind of getting into why it's useful to simulate things like stopping power, it's useful to consider first how targets like this are designed. And to provide a bit of motivation for that, I'll return to my home institution of Sandia National Labs, where you see a figure illustrating the Z pulse power facility, kind of in a very, attractive photographic mode right here, where lots of arcs and sparks are occurring right here in this facility. But essentially, this is a large pulse power facility that we can use to deliver very high currents to small canisters. So unlike the NIF sort of concept for inertial fusion, we're driving these things essentially with very strong currents. And in particular, on the right-hand side of my slide, you'll see an example of essentially kind of cartoons from simulations of a target design for a concept called magnetized liner inertial fusion. It was, some of the first experimental demonstrations of which were published in PRL back in 2014. And this is to kind of show some of the illustrative difficulties, which is to say that the instabilities that you see in, kind of these cartoons that are illustrating, what's actually going on in one of these ICF implosions show, kind of material instabilities that are kind of happening on the way to ignition that essentially redivert some of the energy that you're trying to put into fusion into just hydrodynamic instabilities. And it turns out that this is actually more of a material science or plasma physics problem than a nuclear physics problem, which probably doesn't surprise a bunch of folks who backgrounds in nuclear physics, of course. But this is all to say that one of the bigger challenges in designing ICF concepts, targets, et cetera, is compounded by the fact that the materials that we rely on to kind of crush these little packets of fuel are going to be in extremes of temperatures and pressures that are really difficult to produce terrestrially in a laboratory, let alone to even, probe what those properties look like. So what do I mean by extreme here? Essentially, I have a density temperature diagram that I've taken from Mike Desjardins on this particular slide right here that spans many decades in temperature and density. And you can kind of see from the arrows on my slide right here that your fuel is going to start way down here at essentially cryogenic temperatures and relatively low densities, and it needs to wind up here where there's thermonuclear ignition, right? So you need to cross this enormous range of temperatures and densities, and of course, we know how matter behaves, at room temperature and below, and kind of these sorts of lower densities, let's say, just based off of the fact that it's relatively easy to measure these things. And up here, beyond ignition, things behave pretty classically, and we have a pretty good understanding of how burning fusion plasmas behave. But in between, there's this really challenging regime called the warm dense matter regime that's essentially typified by kind of a competition between degeneracy, so quantum effects, and thermal excitation effects. And it turns out actually that during ICF implosions, like the ones at NIF or the Sandia Z facility, this warm dense matter regime is actually where your target is going to spend most of its time, which is to say that if you get it all the way to burning, then that's great. But during the actual implosion itself, it's mostly hanging out in this weird, very difficult to understand regime. And it's really hard for us to constrain materials models here. And by materials models here, I mean things like the equation of state or the transport properties, the electrical thermal conductivities, or the stopping powers, as it were. Right. And in order to design targets and, kind of fusion experiments like the ones that I've been telling you about, we need to essentially have kind of high-level hydrodynamic models of these implosions that we essentially, tabulate these materials properties over the many decades in density and temperature that are relevant to these simulations. So we need to be able to basically, have something that, in some PD solver somewhere, is looking up at a particular density and temperature what all the different materials properties relevant to the design are. And these aren't really things that, we just have lying around from years of experience. We often rely essentially on theoretical models. So this motivates getting into stopping power as one of the things that we care about. Again, stopping power is germane to, kind of ignition in these ICF experiments. But, more generally, I'm going to tell you a bit about what stopping power is, kind of conceptually before getting into the specifics of what it has to do with fusion. So stopping power is essentially, kind of a property of a projectile, a target, and the velocity of the projectile, which is to say that you can imagine having some projectile with some bare charge and mass that's fixed and some initial energy that you're throwing that projectile at some target, again, at a fixed density and composition, typically in some equilibrium state. And as that projectile passes through the target, it's going to lose energy, unsurprisingly. The energy is going to be lost in collisions with nuclei, electrons, and light. When I say nuclei here, I mean basically, direct nuclear sort of collisions. Primarily, we're going to be talking about electronic collisions today. And it's worth more noting that, collisions with light, Bremsstrahlung, this sort of stuff, this is also capable of being handled. But the thing that we're really talking about today is actually electronic stopping power, which is the contribution of stopping power that's going to be most important to inertial fusion applications. And just to kind of say a bit more, stopping power is the differential energy loss per unit length, which is to say that this actually has units of force, not power. This decision is not mine, so I apologize on behalf of whomever did make that decision. But ultimately, we want to compute a force that this target material is pushing back on a projectile with as a function of the velocity of the projectile, right? So we can calculate this actually from first principles using tools that look an awful lot like kind of the sort of things that people use in chemistry and material science to study electronic structure. In particular, we're going to simulate the dynamics of one of these projectiles, either a proton or an alpha particle, as it passes over kind of a nanometer sort of length scale over order attosecond time scale, kind of a box filled with the material, which is what this movie on the left side of my slide is right here. You're essentially seeing the density response of a proton passing through kind of Pac-Man style, a box of a deuterium plasma, actually, and kind of the wake that it kicks up and thus, kind of deposits energy back into the system with. So again, it's worth remarking here that we're actually doing this, just with first principles electronic structure theory, which is to say that the Hamiltonian that we're concerned with simulating here is kind of the conventional one that you see all over chemistry and material science. You have the kinetic energy, you have the Coulomb energy of interaction between the electrons and the nuclei in your burning plasma. You have the electron-electron interaction between the electrons in your burning plasma. And then you have some contribution due to the kinetic energy of the projectile and its Coulomb interaction with everything else in the system as well. I would say that this is just kind of very standard physics in substance. There's nothing terribly exotic here, but it is still quite challenging to do these simulations. Which is to say that our very best theoretical models for stopping power based off of this sort of first principle simulation approach are quite expensive to run. So on this slide, I have a chart that essentially shows a stopping power curve. Again, this is that force as a function of the velocity of a proton in warm, dense aluminum at a couple of different temperatures from 1 electron volt to 20 electron volt. Of course, an electron volt here in units of Kelvin is about 11,800 some odd Kelvin. So this is, again, quite hot. And you don't necessarily need to understand the distinction between total, free, and core here, though if you ever are interested in reading this paper that we're putting together on these particular results, certainly that will be relevant. But for the purposes of today's talk, it's worth noting that this specific figure right here took about 250 million CPU hours to produce using a $174 million supercomputer that was sitting somewhere in northern New Mexico in Los Alamos National Laboratory. Which is to say that, just producing figures like this is the sort of thing that we use these giant computers for, and we use these giant computers at scale to do these calculations. So this kind of motivates, at least it begins to motivate using a quantum computer here, another big, expensive hypothetical machine here. Now, we don't actually use really expensive models like this, these 250 million CPU hour calculations, in order to do hydrodynamic modeling, but we do use them to check the models that are used in hydrodynamic modeling, right? Which is kind of what I'm going to tell you about now. Unfortunately, the accuracy of these models is a bit difficult to assess, which is to say that that last slide was focused on aluminum in part because it's an ideal system for benchmarking, but we don't necessarily really understand the accuracy of the model all that well. And this also motivates the potential benefit of a quantum computer, is having a source of kind of an unbiased, higher accuracy sort of estimate of what these forces are. On the left-hand side of my slide right here, you see a stopping power curve for conventional condensed phase, cold dense matter, standard aluminum, comparing essentially some calculations that we did at Sandia, some calculations that our friend Andre Schleife et al. Did at the University of Illinois, and the SHRIM database, which is to say that we can essentially find good agreement between two different theories and experiment and conditions in which we can check it. But we don't always have a great sense for how systematic the errors are. And on the right-hand side of my plot right here, this is kind of an assessment of finite size errors in these calculations that we're doing. And up until about basically this paper that we wrote back in 2023, there was kind of this very simplistic sort of Lindhard style dielectric picture of how finite size errors should impact these types of simulations. And we actually went in and did some validation of this and found essentially that the calculations that we're doing they aren't consistent with kind of, what was conventionally received as the wisdom for, how finite size errors impact this. So this is all to say that, there are things about classical computations in this particular regime that we don't really understand that well. This is compounded by the fact that this is all done in kind of condensed phase systems that, we can produce in a terrestrial lab here for relatively cheap. And experimental data in this warm dense matter regime that's ultimately very important for fusion is actually extremely sparse. And to show you a bit of that, I'll tell you how we actually measure stopping power in warm dense matter. It'll give you an idea of just how expensive that is in some sense. So I've taken a few figures here from a 2015 PRL. There seems to be a question, or?
Hi, Andrew. Yeah. So can you go back a slide, please?
Yep.
So I'm just not familiar or don't remember what atomic units. So in units of say MeV, what is the proton velocity? What's effectively the energy of the proton here?
It's somewhere in the vicinity of tens of kiloelectron volts, I believe.
Okay, so keV total below MeV.
Yeah, so it's distinctly non-relativistic.
Okay, great, thank you.
I hope I did that conversion all right on the fly. So yeah, but yeah, I should be within about a factor of 10, I hope. So yeah, all right. So getting to back to experiments at least. This is results taken again from a 2015 PRL, from a group at MIT working with a bunch of folks, but ultimately this experiment was done at the Laboratory for Laser Energetics at the University of Rochester. And this is one exemplar of how stopping power is measured in this regime. So essentially you build kind of a mini ICF target that you can drive using the very high intensity lasers at the LLE. To essentially produce a relatively monoenergetic source of protons. In this case, you're looking at protons that are moving actually quite a bit faster than what I just cited on the past slide. So in this case, you're kind of very high up on what's known as the Bragg curve for stopping here. You're talking about protons that are coming out at 14-ish mega electron volts. And this beam of protons is then going to be aimed at a beryllium plug that is surrounded by essentially a silver coated tube that's also going to be illuminated by the high intensity lasers at LLE. And the corona essentially of plasma that comes off of this is going to emit, there's going to be L-shell emission from the silver. It's basically going to bathe this beryllium plug in X-rays that's going to isochorically heat it to the warm dense matter regime. I believe in this paper, the original estimates for the temperature were somewhere around 30 electron volts of temperature, though that's come down a bit in recent years through analysis. And you can basically measure the energy loss as this monoergic beam passes through the beryllium plug, both as a function of, whether essentially the plug was warm or cold. And you can compare the experiments, again, in the cold and warm regime to different, the experiments of the colored data here, and the theories are the not so colored data. And what you see, at least in the warm regime, is that, okay, there's at least one point of agreement between one particular theory that is actually based off of density functional theory. But, also there are other shots that seem to deviate, systematically from things. There's still uncertainty here. The point to take home from all of this is that this sort of experiment is very expensive and time consuming to do, and it gives you a relatively small amount of data that's far from comprehensive. It turns out that right now there are fewer than about a half a dozen data sets that constrain stopping in this regime. And again, these are using, multi-$100 million to multi-billion-dollar facilities to actually produce, relatively sparse data. So again, a motivation for a quantum computer. Okay, so we're returning now to this program of first principle stopping power calculations, where essentially we want to make some representative supercell of some burning plasma. And we want to drag a projectile through it at a fixed velocity so that we can measure essentially the work or force done by the target on the projectile as it passes through. That representative supercell in this case is going to consist of tens to thousands of atoms or electrons. So the particular illustration right here is about 1,025 atoms and, I don't know, a couple thousand empty bands or something like this. And we're essentially going to take such a representative supercell, insert a projectile, and move it through so that we can basically go back and calculate, using whatever electronic structure theory we have, either, again, the work that the plasma is doing back on the projectile, or the force that's pushing back on it equivalently, kind of a Newton's sort of thing. This is the stopping power. This is how we get it, from first principles. In spite of the fact that the thing that I showed you on the last slide was kind of a macroscopic thing, we can actually estimate these things from relatively small supercells. And we do this using time-dependent density functional theory. I won't say too much about what TDDFT is, other than to say that this is essentially the nonlinear kind of mean field-like equations that govern it. I know there are a lot of, there's a deep well of expertise in TDDFT at UW, so maybe some of you even know more about TDDFT than me in the audience. Or, well, yeah, bad sentence there, but yeah. Anyhow, TDDFT is essentially going to take the form of a mean field theory where there's some exchange correlation contribution to the mean field potential that you have that's going to be density dependent. And this is essentially the central approximation. It's possible in principle and in practice to come up with the exact potential given a lot of computational resources, but there are many features here that are difficult to approximate, which is to say that TDDFT is essentially in principle capable of simulating the electron dynamics exactly, but in practice it is very difficult, right? And this is kind of the state of the art for how we do the electronic dynamic simulations that are used to generate kind of our 100 million hour TDDFT calculations. So this motivates, okay, we have the classical state of the art here. What could a quantum computer do for us? So this is where some of the collaboration with Google starts to take off that I mentioned. This was one of the first papers that kind of started to stake out what it might be that a quantum computer could offer over a classical computer in this regime. So TDDFT, again, has the form of a mean field theory, which is kind of like time-dependent Hartree-Fock, which is, a proper mean field theory, let's say. And in either of these, we're propagating the dynamics of essentially a single Slater determinant. The electrons are going to live in the single Slater determinant, and they're going to react to some external perturbation. As I mentioned before, TDDFT is practically limited in its accuracy. You could make it exact in principle. It's very hard. There are complexity theoretic things at work here. And TD Hartree-Fock is fundamentally limited in its accuracy. But this is all to say that these two mean field theories are generally going to be the least expensive and least accurate levels of theory that you can afford. And for the large shells that we're looking at simulating on our supercomputers at Sandia, it turns out that this is kind of all we can afford, actually, is this level of theory. So one of the initial results that kind of spurred some of the work is this 2023 paper led out of Google by Ryan Babish et al. Essentially analyzed the asymptotics of a bunch of different mean field theories and showed essentially that there are quantum algorithms for exact dynamics, not approximate dynamics, that actually have better asymptotics than classical algorithms for mean field dynamics. So it's often the case that we think of quantum advantage for dynamic simulations as being kind of this exponential-like advantage, let's say, between exact dynamics on a classical computer and exact dynamics on a quantum computer. In this case, what we're essentially showing is that there is a quantum advantage, albeit a slightly superquadratic one in some regimes, where you have exact quantum dynamics beating out even kind of the worst in kind of a good faith notion of worst, accuracy kind of classical algorithm right here. So you still have sort of a putative exponential advantage over the exact classical solution, but you also have polynomial speed up even over kind of the least accurate classical method in some sense. Of course, you can think of least accurate in a lot of ways, but this is kind of a good faith notion of that. So this motivates developing, in detail, a quantum stopping protocol. How can we actually go and make this reality, take these quantum dynamics algorithms and calculate stopping powers with them? So a really naive approach to this would be to just do everything that we would do in a TDDFT calculation, but using our favorite quantum dynamics algorithm to kind of propagate everything in time. So there are a couple of problems with that. We just say that one thing you might imagine doing is estimating the energy as a function of time. So, propagate the projectile for a couple of different times and basically see how the energy goes up as a function of the amount of time that you're evolving, basically the thing on the right here, right? It turns out, though, that energy estimation is expensive, right? So you might say, okay, well, the energy estimation is expensive. Why don't I just look at the projectile force, again, at multiple evolution times? Again, kind of the other, plot here. on the right-hand side? Well, it turns out that the force operator is going to have a large norm or variance, depending on how you estimate its expectation value. The norm is relevant, of course, to block encoding-based observable estimation. The variance is relevant to kind of estimating at the standard quantum limit, typically. So, okay, that's great. So kind of the conventional things that we think to do aren't necessarily the best thing to do. Otherwise, another thing to account for is the fact that updating the projectile position, the way that we would do it in a time-dependent DFT simulation, actually introduces a time-dependent simulation. So we're going to treat actually the projectile as an autonomous quantum degree of freedom that is going to allow us to use time-independent Hamiltonian simulation instead. So that's all to say that the quantum algorithmic protocol that I'm using is kind of sidestepping these things that you might try to do if you were just kind of trying to copy TD-DFT directly, which is to say that the solution is essentially to wind up making this projectile an explicit quantum degree of freedom that evolves autonomously, no time-dependent simulation, and to estimate the kinetic energy of that projectile degree of freedom explicitly as encoded in a specific register in our simulation at multiple evolution times. This is kind of the best way to go about doing this, actually. Please, question.
Hi, yeah, I just wanted to clarify. So the objective is to not actually use a time-dependent Hamiltonian. You do want to go towards a time-independent one. Is it because
Correct.
it's...
Yeah, sorry.
Oh, yeah, is it because it's cheaper? Computation?
Effectively, yeah. The algorithm is easier to implement, and yes, it would be cheaper. Though there are not explicit estimates of the time-dependent simulation costs in the paper that I'm talking about. Yeah, the general expectation is it would be. So yeah, now I will essentially get on to describing our algorithm in a bit more detail. So the protocol consists of the following steps. In the 0 step, we choose kind of representation of this system, our supercell, the target and projectile material systems. The first step after that is to prepare an initial state for the electron projectile dynamics, basically to time evolve the projectile moving through the electrons and nuclei in the plasma. Step 2 is implementing the actual time evolution itself. We're going to look at qubitization, incidentally consider interaction picture, and also consider trauterization, kind of standard approaches to doing time-independent Hamiltonian simulation. Then we're going to measure the projectile's kinetic energy loss along its trajectory, and from that, post-process the sampled outcomes classically to estimate the stopping power. So these are, kind of the usual things that you do in any quantum simulation algorithm. Choose how you're going to represent the system, state prep, evolve, measure thing that you care about, right? Nothing too crazy here. So getting to step 0, the representation of the system, we're going to work in first quantization, which is to say that each quantum particle in the first quantized representation is going to be described by a register of qubits that encode essentially a plane wave basis for that particle. On the right-hand side right here, you can kind of see that, those plane waves are going to be indexed by, 2 pi divided by the volume of the system times some integer index that lives, basically it's actually a triplet of integer indices. They're essentially going to describe plane waves of different wave numbers. So essentially each quantum register is going to have a bunch of these integer triplets that are going to essentially correspond with different plane waves, right? This basis, it was first studied in a quantum setting in this 2019 MPJ-QI paper by Ryan Babish et al. And the block encodings attendant to implementing kind of the Hamiltonian that I showed you, several slides ago, are also expressed in 2021 PRX Quantum article by Yuan Su et al. But this is all to say that the representation of the system is basically just some big box of volume omega that has a bunch of plane waves in it, and we're going to use essentially a register with log n to the 1/3, 3 times log n to the 1/3 qubits in it to essentially encode the electronic state of each degree of freedom here, which is to say that overall the number of qubits that we're going to need with eta electrons and 1 projectile with a slightly different cutoff, let's say, for the projectile, is essentially going to scale linearly in the number of electrons and logarithmically in the size, the number of plane waves. So that's actually quite nice in the sense that that's actually an exponential advantage in memory in some sense over the classical algorithm as well. The non-projectile nuclei, you might be wondering why I'm not accounting for those in this sort of resource accounting, and that's because they're not going to move appreciably over the very fast timescales associated with electronic stopping. So we're just actually treating them as effectively fixed in the simulation. But the projectile is moving about as fast as the electrons, and thus we need to basically treat that, its motion explicitly. It's kind of the whole point in some sense. And it's worth noting that our paper has some non-trivial extensions of the block encodings in this paper in it. And if you're really into block encodings of first quantized simulation, I encourage you to look at the article to see kind of how we deal with having different kind of plane wave grids and things like that for the electrons and the nuclei. But this is all I'm really going to say about the first quantized representation. From here, we need to now be able to prepare the initial state. And there are two subsystems that we need to care about for the initial state. One is the electronic subsystem, and the other is the projectile subsystem. On the electronic subsystem, we're going to essentially want something that looks like the Gibbs state, basically the thermal equilibrium state at inverse temperature beta right here. What we're doing, we're not using any of these terribly sophisticated kind of like Lindblad-based, sort of thermal state prep algorithms. We're actually just going to kind of use a mean field initial state from a Merman-Kohn-Sham density functional theory calculation and generate a canonical ensemble over that set of Slater determinants, right? So basically we have, some mechanism by which we can efficiently calculate, kind of the probability of drawing any given microstate that is going to be the initial state for our electronic dynamics. And that's kind of it. So on the electronic side, it's basically just going to be drawing these Slater determinants from that ensemble. And of course, this relies on efficiently preparing Slater determinants. And there's some novelty in actually that exact quantum dynamics article that I cited again from Ryan Babish et al. Back in 2023 that's relevant right here to actually preparing these Slater determinants in first quantization. But that's kind of the end of it. The other subsystem that we need to deal with is the projectile subsystem, and that's going to be basically a Gaussian wave packet in momentum space. And that Gaussian wave packet is going to be sharply peaked near the projectile velocity in some sense. Now, this kind of suggests the question of what the variance of that wave packet is, and that's actually a free parameter. You could imagine, kind of taking the variance of that wave packet to correspond essentially, inversely to, kind of the physical real space dimension of a proton. But it turns out actually we can, doing some math or whatever, actually in practice make that variance 10 to the 4 times smaller than a physical proton. And this is like kind of a reciprocal space thing. So really actually our quantum degree of freedom is about 10,000 times larger than a physical proton in real space, which is to say that kind of the Coulomb interaction that we care about is in some sense smeared out over a relatively large length scale compared to the size of, an actual physical nucleus. This relies on our ability to prepare Gaussian states, and that's basically, this is a citation by which we come to the resource estimates that we use in this paper. So again, thermal states on the electronic subsystem, Gaussian state that's basically representing the wave packet of some proton moving through our system on the projectile subsystem. That's the initial state. Now we need the time of all of that. We considered 3 different approaches to time evolution: cubitization, interaction picture, and trotterization. Cubitization and trotterization are kind of in competition here. Cubitization is easier to analyze. Trotterization is harder to analyze. Interaction picture wasn't actually competitive here, so there aren't really a whole lot of things to say other than, it's kind of a competition between the other two. Our cubitization-based approach is basically using quantum signal processing on a block encoding of the first quantized Hamiltonian that I've shown you to implement the Jacobi-Anger expansion of essentially the exponential propagator. And that block encoding, it's worth noting, also includes the projectile in it as well. So it's not just the electronic subsystem, it also has to include the projectile because the projectile is moving as well. It's an autonomous degree of freedom. But this is essentially the cubitization approach in, one line, right? Trotterization proceeds about as you would expect it to proceed, which is to say that the kind of complicated and difficult thing in trotterization here is to essentially calculate inverse square roots. We're going to use QROM interpolation and Newton-Raphson iteration to calculate inverse square roots for the Coulomb interaction. And that's, kind of the hot part of our algorithm as far as the costs are concerned, and some of the novelty that's actually in the paper, new ways to do this computation more efficiently. And it's worth noting that Also, there was a lot of numerical testing that went into estimating the constants for tighter trotter bounds based on some work by Guang et al. In this 2023 PRX Quantum article. This is all to say that we have some pretty good numbers, I think, for what the trotter costs are for time evolving this system. They're, kind of maybe at the state of the art in some sense right now. So we're kind of comparing, again, qubitization and trotterization. As far as resource estimation is concerned, we have kind of all of the things that we need in order to understand kind of the overall costs of the different approaches to things. So one of the really cool things our collaborators at Google did was they have this software package that, if you haven't seen it before, I encourage you all to go out and look at it. It's called Qualtran. It was used to build and profile, essentially model the entire protocol. So you can kind of go through subroutine by subroutine and see what the Toffoli counts are for each of these. And, just for the sake of completeness, Toffoli is here some metric for the overall non-Clifford resources required to implement our algorithm and kind of the dominant cost of a fault-tolerant, quantum simulation implementation here. It turns out for the qubitization-based approach, the dominant Toffoli cost is actually a subroutine that involves applying controlled swaps to move each electron into a working register during the select in this sort of block encoding procedure. So we can kind of see that outpaces everything else by about 2 orders of magnitude, actually. And this is just kind of a cool tool. You can actually see the costs broken down in kind of, a very fine-grained form like this. And just, again, for the sake of completeness, the inverse square roots are kind of the hot spot in our trotter algorithm, actually. So that's kind of the thing that, is equivalent to the large Toffoli counts in the trotter, right? Might warrant noting that, they're going to be sort of eta squared of those, the usual problem of pairwise interactions. So it's kind of the dominant thing in some sense. Now that we have kind of all the pieces together for, state prep, time evolution, and, understanding the cost of all these things, we now want to know how to measure the kinetic energy of the projectiles being stopped, essentially. And here we compare estimates for the kinetic energy lost based off of essentially sampling at the standard quantum limit. So in first quantization, we literally have a register that's going to be indexing essentially the kind of momentum distribution of our projectile, and basically just measuring in that basis is going to give us some estimate very directly of what the kinetic energy is at the moment that we're doing that measurement, right? So we're comparing that sort of very straightforward standard quantum limit sort of approach to a recent Heisenberg scaling approach by Kotari and O'Donnell, this KO algorithm, or knockout as we sometimes call it, I guess, kind of, well, yeah. And the nice thing about the KO approach is that it achieves Heisenberg scaling, and it also has a factor of essentially the variance of the variable that you're estimating the expectation value of in there as well. But what you see on this plot here is essentially the Toffoli cost for estimating kind of an end-to-end sort of kind of the kinetic energy of basically one of these time-evolved simulations as a function of the target accuracy, epsilon right here. And it turns out actually that for the accuracies that we care about, in order to beat a classical computer, it turns out actually that this standard quantum limit sampling suffices, which say that we need actually relatively poor accuracy to kind of beat the classical computer. Though if we needed to go to higher accuracy or smaller epsilon here, it turns out that the Heisenberg scaling approach will eventually win out. But this is all to basically say that we kind of worked out the best way in some sense, given our algorithm at hand, how to estimate the actual thing that we care about for, estimating a stopping power. Which brings us to actually computing a stopping power from the samples that we're getting right here. And in order to assess kind of how those sampling requirements affect the overall overhead, we essentially used a classical Monte Carlo estimate on a classically computed TT-DFT trajectory with kind of a fixed projectile variance that models essentially the variance that we expect in the quantum simulation. And this is the sort of stopping curve that we expect to see for essentially proton stopping in one of these plasmas. And pardon me. What we essentially see is we can actually just look at how many shots we're going to need to kind of converge things using something that looks what we expect like real data will look like when you actually have a fault-tolerant quantum computer to actually implement this sort of thing. So that kind of gives us an end-to-end sense for exactly how long it's going to take to get one of these estimates of a stopping power out of these calculations. So we have, really, kind of fully costed this algorithm out. So that kind of brings us to the end, which are resource estimates for fusion relevant systems. So this table right here has a number of different projectile target pairs, and basically gives the number of electrons in each of these. So we go from basically a small system to a relatively large system. And then we essentially have Toffoli counts and logical qubit counts for the two different time evolution approaches that I mentioned. So both the qubitization or QSP-based time evolution and the Trotter product formula time evolution. It's a bespoke 8th order formula actually right here. And what we find is that in general, the product formula outperforms, actually, the Trotter formula outperforms the qubitization approach in general by, even a order of magnitude here, and it grows, of course, as you go higher up. And in qubit count, they're somewhat comparable in some sense, though it is worth noting actually that the product formula qubit count is higher than the QSP qubit count, which I think a lot of people find confusing. So I'll just cut that off and say that, the reason that there are more qubits for a product formula is because essentially doing the arithmetic, the QROM interpolation and all this sort of stuff actually has a qubit overhead to it. So it's actually more severe than the qubit overhead associated with qubitization. But this is all say that we have the resource estimates accounted for right here. And for the smallest instance, the Toffoli count is about 2 orders of magnitude from the state of the art for quantum chemistry problem FOMOCO that probably a lot of you have heard of. That is kind of the gold standard for resource estimation in at least kind of quantum chemistry sort of settings. And I've taken a figure right here to kind of lay things out, kind of all together, where you have this alpha plus hydrogen stopping power result that I've just quoted right here in terms of the circuit depth and the circuit width. Way out here, molecular energy estimation for FOMOCO, integer factoring over here, again, estimates from Google, and then kind of NISQIR data down here that's actually taken by my collaborators at the Quantum Performance Lab here at Sandia. And kind of this is just showing how far off we are from actually achieving this, which is probably not so surprising to everyone, but I think it's kind of cool to see this all laid out, kind of a roadmap in some sense from, essentially where we are today, where we aspire to be, and, kind of the resource estimates that we have for these sorts of big problems that we hope to solve using quantum computers. I'll note that, even in this small instance of 28 electrons in a large basis set, simulating non-equilibrium dynamics of that problem is still going to be very classically challenging. I would hesitate to say that it's classically intractable because I think that people have a high standard for what that means nowadays. But it also tells us, we could do the simulation, and even if it wasn't possible to certify that this was some, sort of quantum advantage right here, it would tell us an awful lot about how mean field approximations like TD-DFT fail. So that's all to say that even this smallest instance right here would be pretty useful, I think, as far as, motivating the development of a quantum computer for kind of fusion science. And just to kind of give a bit of classical perspective that I think is kind of cool is, if you remember, I mentioned that, we're running these calculations on these $174 million machine at, Los Alamos. There's another expensive machine nowadays that we run these things on, also at Los Alamos. But if you take 10% of the 40 petaflops that old machine was running at, which is roughly what our calculations are occupying, 10% of that machine for about a week, which is again how long the calculations take. That's about 2.5 times 10 to the 21 floating point ops. So the number of actual floating point operations that supercomputing is doing is actually predicted to be larger than the number of kind of more elementary Toffoli sort of operations that are required for implementing these quantum simulation algorithms. And again, this is kind of the worst sort of mean field calculation right here. So even if these numbers look crazy, I think it's useful to put it in perspective and to say that, classical supercomputers are doing an awful lot of work. And, these big numbers are actually still smaller than this big number. So I think that that's pretty cool. Please.
Than which the mean field approximation is kind of okay or kind of correct? Or is it just wrong from t equals 0?
I would say that it's not been well analyzed for this particular problem, in part because it's difficult to go beyond the mean field approximation kind of at scale. Certainly if, you could do, some more sophisticated time-dependent method that, could kind of validate the results of the mean field calculation, classically, then you might be able to say something. But in this case, it's kind of shooting in the dark in some sense. It's, you know, in order to do these large calculations, we kind of need to resort to that approximation, and we expect it to be pretty severe, but we also know that it happens to work pretty well in practice. It's just hard to kind of make quantitative, if that makes any sense. All right. So this gets to kind of the last slide where I just can allude to some ongoing work. We're also doing resource estimation for other problems in astrophysics and planetary science, kind of coming up with quantum algorithms and working through what it'll take to actually solve some problems of interest to the DOE. So on the left-hand side right here, iron opacity and solar atmospheric conditions actually is something, again, one of these things that we use very expensive experimental facilities like the Z facility here at Sandia to actually measure. And even when we do the measurements, there's controversy between, you know, other measurements and theory and so on and so forth. So right now, my colleagues Shivesh Padak and Lena Kononov and I are working on a result basically to calculate this, you know, using a quantum computer and kind of resource estimates attendant to that. Where we're seeing our results that are a bit less severe actually than what I've just quoted for stopping power. So that's encouraging. Otherwise, there's a fun kind of planetary science problem related to the electrical and thermal conductivity of iron in planetary conditions. It turns out there's about a 2 billion year spread in the predicted age of Earth's inner core based off of 2 different sets of measurements of the thermal conductivity of iron in these conditions. So this is, again, another context in which a quantum computer could maybe bring to bear, you know, some sort of decisive, you know, sort of highly accurate, you know, insight from theory that, you know, might help to settle some scientific disputes, though that's a bit less applied than fusion. But with that, I've kind of gotten to the end of my talk. So I will open the floor to questions. And yeah, I really appreciate, I guess, your engagement. Thank you.
So thanks a lot. We have time for questions. Questions from the audience, just raise your hand.
Yeah, Andrew, that was really nice. Thank you. I'd like to understand a little bit better why, what was the problem with doing the, you know, dragging a background charge along at constant velocity through the plasma to look at the EDX? What was the additional cost associated there that made it so you would actually then prepare a wave packet and evolve that entire system?
The extra cost is essentially accounting for the fact that the Hamiltonian is now going to be updated each time step to reflect the fact that you're, you know, moving basically one of the Coulomb centers as a function of time. And it's probably not that huge of an overhead, but then you get into different types of analyses for the Trotter error and so on and so forth. And also, at least in the case of the cubitized algorithms, you know, I guess there are results for combining kind of cubitized approaches with time-dependent Hamiltonian simulation. But in this case, you know, we don't need to. We can just, you know, add it as an autonomous degree of freedom, and then it's a time-independent simulation there. So it kind of makes the cubitization analysis easier, and it makes the Trotterization analysis easier. And you know, we do expect in general that, you know, kind of updating the Hamiltonian each step might introduce some added costs, but that depends on the method and so on and so forth. So it's not like a fatal flaw in some sense. It's more or less just this seemed like the best solution.
Okay. All right. Thanks.
Any more questions also from the online audience? Just raise your hand.
Yeah, sorry, I got another one for you. So what is the dominant loss mechanism?
It's essentially the excitation of plasmons in the plasma. So essentially, once that projectile is moving around kind of the average thermal velocity of the electrons, it will essentially start to kick up a wake, you know, in terms of kind of the plasmons that it's pushing. There are some single particle excitations and things like that that are also being excited, but it's mostly the collective excitations that matter the most kind of in the regime that we care the most about stopping in. So.
Okay. All right, thanks.
We have time maybe for one or so questions if there's somebody online. If not, I could ask maybe a question. So you have a good estimate how large relativistic corrections are that you're not taking into account in your simulations? And if so, if there's a way of basically adding them?
So kind of the leading thing would probably be the Bremsstrahlung, and that's going to occur at much higher energies. And there, kind of classical relativistic electrodynamics will give you a decent estimate of what that contribution would be, albeit, there is some amount of screening by the plasma and so on and so forth. But, there are decent models, I would say, for kind of Bremsstrahlung. For heavier nuclei moving faster, harder to say. It's actually something I'm less familiar with, but at least for kind of the case that we're most concerned with for fusion of kind of protons and alphas at kind of moderate velocities, moderate non-relativistic velocities, kind of the biggest correction would, I think, be the Bremsstrahlung, but hope that kind of makes sense.
Yeah.
Cool.
I have another question, actually. Sorry, so I got another question for you. So the physics picture that I have from what you're doing is I create a wave packet initially of a proton that's tensor producted with the slated determinant construction you have, the electronic medium, basically a Born-Oppenheimer approximation of their medium, the nuclei are fixed in place, and the electrons are free to move. And then the systems evolve forward with electromagnetic interactions. And then later on you measure, this is my question, so you measure the 3 momentum of the proton at some later time t.
Yep,
and
exactly.
Measure and then whatever the difference between what the momentum was initially, the energy was initially, and the energy at that time t, that'll give some distribution that's then averaged to give you the average value of the energy loss, and that gives you some error bar or something like that.
Correct. That's exactly, yep. That is what we're doing, or proposing to do, rather, albeit in these kind of simulations, let's say the quantum protocol, that is essentially what we're doing. Yeah.
Right. So the any of the momentum that's sort of in the electromagnetic field that's tensor producted off as being part of the medium and not part of the proton. So I'm saying if the electromagnetic coupling was much larger, there'd probably be some non-perturbative effect that's not accounted for correctly. But with weak coupling, you just tensor product it basically and ask how much is in that momentum state, even though there's probably an engaged invariant answer.
Yeah. So I think I hope it's addressing the same point that you're bringing up, but we could say introduce an explicit sort of photon field if we wanted to, and kind of we could introduce coupling to the EM field explicitly, but in this case, kind of for the velocities that are relevant, kind of this sort of non-retarded sort of very Coulomb-y sort of interaction suffices. Does that kind of make sense? Okay, so at very, very low velocities, this is probably not. Yeah, it's a tiny thing. So, yeah. All right, yeah. Good, thanks. And I now appreciate that what constitutes a high and low velocity is highly relative, and when talking to a nuclear physics audience, this probably all seems very off in that regard. Yeah. So I guess for material science, this is very high velocities. Yeah, exactly. Yeah. Okay.
All right, so I see no more questions. Let's thank Andrew again.